Let's talk about non-ideal effects in op-amps. First of all, the differential gain, AD, is less than infinity. The output resistance is greater than 0. The input resistance is less than infinity. The common mode rejection ratio is less than infinity. Those are all things we discussed before in some brief way. Now, the second thing that we want to look at here, first really kind of new thing, is the power. To power the op-amps, we need batteries. And these batteries are DC voltages, here denoted as V sub CC and V sub EE. Now, linearity would indicate that a battery will cause a DC output voltage. In general, if you have several input voltages, superposition says the output will be partly due to each of these, and that's what this equation shows here. The red part is the part due to the power supplies, and it's called the output offset voltage. Ideally, it would be 0. We note it as VO sub off. Here we have another picture of something that happens because you're running this on DC power supplies that are limited. In general, the way the op-amp works is it can never put anything out bigger than the positive DC power supply or smaller than the negative DC power supply. And an input-output curve you see here is somewhat typical. There will be, as we discussed before, a y-intercept of V output offset. And you can see that here in red, right here. There is a phenomena that's happening up here. It's curving over because it can't get bigger than VCC, and it's curving back under down here because it can't get less than negative VEE. This is a nonlinear transfer characteristic. If it were linear, it would be a straight line that would go right through the origin here and have the same slope everywhere and would not be limited by VEE and VCC. It's probably fairly close to linear right here for very small Vn. So one way we can describe this curve is using a Maclaurin series. You see that done down here. We have V output offset is due to, V output is due to V output offset right here, plus the amplifier term, AD times V sub I. And then you have some higher order terms. This is the second order term, K2VI squared. And we have K3VI cubed, that's the third order term, and so on. Many more distortion terms. So these higher order terms will allow this thing to curve over here and to curve under here. Another way of looking at this is if we suppose the input voltage was sinusoidal, like VI equals cosine omega t. If you add something like that, if you put a cosinusoidal wave in here, when you're wiggling your cosine back and forth on the input axis right here, it's wiggling your output back and forth on this. And notice that you might wiggle your cosine over in this region right here, which would not put out the voltage you were expecting, which would be down here. It would put out this voltage. So that tends to clip off the peaks of the cosine wave on the output, making it look more like a square wave. Here we have a picture of that in time. Black is the input voltage, and the orange is the output voltage divided by AD, so we could write them on the same scale here. Now, when you have a voltage like this kind of squarish wave right here, it is a periodic waveform, and it can be written in a Fourier series as denoted up here. So to get an idea how that might work, the n equals 1 term is somewhat like the input here. It's black, like the black input. The n equals 2 term is not present in this square wave here. The symmetry doesn't allow that to happen. But the n equals 3 term is present in this square wave. And it will cause the black wave to be added to in this region, to be subtracted to when it's right here at its peak, and to be added to here, and to be subtracted to there, and added here and subtracted here. It's going 3 times as fast as the black wave because it's cosine of 3 omega t. And then you can have fifth and seventh and ninth terms as well. They all get smaller as the subscript on the K gets higher, or the subscript on the B sub n on the N gets higher. In general, not necessarily, but in general. So you can actually relate these two ways, the Fourier way and the power series way, together by remembering this nice trig identity. Cosine A cosine B equals a half cosine of the sum plus a half cosine of the difference. If you apply that a couple times to cosine, so you would find something like this. Cosine of omega t cubed is approximately proportional, or is proportional to cosine 3 omega t. And in general, that means the B3 term here is approximately proportional to the K3 term here. Now, it's not exact, because what happens is if you use this thing on the cosine of 5 omega t instead of cosine of 3 omega t, and cosine, or if you do it on cosine 7 or 9 or all those other terms, you'll find that they also could have a cosine cubed omega t in the output, which would have a cosine 3 omega t in the output. And so this is K3. It really does correspond or proportional to B3 in the case where the K 4, 5, 6, 7, 8, 9, 10 and all those are very close to 0 compared to the K3 term. Now, these extra terms in this Fourier series are called harmonics. And so when you have extra terms like B sub 3 is not 0, B sub 5 not 0, B sub 7 not 0, those would cause what we call harmonic distortion. Often amplifier manufacturers give you a specification to try and denote how linear their amplifiers are. One spec would be to give you the harmonic distortion, but often they give you this other measurement too, called the third order input intercept. So what do they mean by that? Well, if you take and make a plot of Vin versus Vout here in a logarithmic fashion, so I'm plotting Vin in dB relative to a milliwatt. So dB is a logarithmic thing, and dB relative to a milliwatt is how many dB a thing is greater than a milliwatt. Like, say, 0 dBm would be 1 milliwatt. 20 dBm would be 100 milliwatts. Minus 20 dBm would be 1/100th of a milliwatt. So that's how the x-axis is plotted. The y-axis is plotted similarly. It's Vout plotted in dBm. And so if you take a spectrum analyzer and you look at the frequency coming out when you put in cosine omega t, the first term here will be roughly proportional to the amplifier term. And if you do it for small Vn, you will find you have a straight line like this with a slope of 1, because you're plotting cosine omega t, the magnitude of that, in logarithmically against itself. And so you'll end up with a thing here, except one of them is multiplied by AD, so that gives you an additive constant here. Now, if you do the same thing with the cosine of 3 omega t, which is really K3 Vn cubed, you're plotting the Vn cubed on the y-axis here in logarithmic fashion versus Vn here, and that gives you a slope of 3. And the y-intercept is K3 in dBm, or K3 in dB relative to 0 here, the way I've drawn it. So the thing that's important here is this point up here where the two lines cross. That's called the third order intercept point. And if you drop that third order intercept point down to the x-axis, in other words, take the x component of that, or the x measurement on that point, that is called the third order input intercept point. You could also take the y measurement, or it'd be over here, it'd be the third order output intercept point, but generally they give you the input intercept point. And the further that is to the right, or the larger that number, the more linear your amplifier is. So that gives you a little bit about the effects of distortion coming from the fact that the amplifier cannot output a voltage bigger than VCC or smaller than VEE. In the next video, we'll look at what happens much more carefully on the V output offset voltage and try and relate that to input parameters, which are usually specified in the op-amp manufacturer's data sheet.